Welcome to this explainer. Today, we're going to unpack absolutely one of the most vital concepts in modern distributed systems, and that's partitioning. Honestly, if you've ever wondered how the internet's biggest apps keep running smoothly when their data just scales right into the stratosphere, well, you're in exactly the right place. Let's get right into it.
Picture this scenario for a second. You've engineered this fantastic back-end, right? But then boom, your application goes viral. Suddenly, your single database server is totally running out of CPU, memory, and storage capacity. I mean, it's literally redlining. So what's your next move?
Here's our agenda for today. We're going to cover the single machine bottleneck, what is partitioning, key range partitioning, the hotspot problem, hash partitioning, and finally, matching your workload. Section 1. The single machine bottleneck, the vertical wall. You know, our first instinct when we hit a wall like this is usually just to buy a bigger, more powerful server. In engineering, we call this vertical scaling, or scaling up. And hey, a massive machine with dozens of CPUs and terabytes of RAM sounds pretty great, right? But here's the catch. The cost grows way faster than linearly. A machine that's twice as powerful is going to cost you way more than twice as much. Eventually, you just hit this massive financial and physical wall, where you literally cannot build a server big enough to handle your heavy network traffic and query throughput. Moving on to Section 2, what is partitioning? Scaling out horizontally. So if we can't just build one giant machine, we have to scale out horizontally. Partitioning, which is often called sharding in systems like MongoDB or Elasticsearch, is simply the process of intentionally breaking a massive dataset down into smaller, totally independent pieces. By assigning these smaller partitions to different nodes in a shared nothing cluster, we actually distribute the load. The theory here is pretty straightforward. 10 nodes should be able to handle 10 times the data and 10 times the read and write throughput of just a single node.
All right, Section 3. Key range partitioning, sorting data by key.
This visual right here perfectly illustrates key range partitioning. It's just like an old-school print encyclopedia. We assign continuous, sorted ranges of keys to specific nodes. Think about it. If you're looking for a word that starts with the letter M, you're not going to read every single book. You just pull the exact volume containing the M range right off the shelf. In a database, it's the exact same concept. If you know the boundaries of your key ranges, you can route a request directly to the specific node that holds that piece of data. So the real superpower here is that because the keys are kept in a perfectly sorted order, reading sequential data is incredibly fast. Just imagine an application tracking a bunch of internet-connected sensors where the primary key is a timestamp. If you want to fetch every single sensor reading for the entire month of October, the database doesn't have to hunt around. It just performs one continuous, super efficient range scan across the specific partition holding October's data. Section 4. The hotspot problem, when traffic jams occur. Now, let's think about the real world for a second. Data access is almost never perfectly even, right? I mean, a dictionary has way more words starting with S than X. So I want you to imagine what happens to our beautifully partitioned database when the incoming traffic isn't evenly distributed. Well, it creates what we call a skewed workload. Let's go back to our timestamp sensor data. Because time only moves in one direction, every single new sensor reading coming in right now is writing to today's date. That means all of your write traffic is just hammering one single partition. Or picture a social media platform. A huge celebrity with millions of followers posts an update, and suddenly millions of users instantly request that one specific record. The result? A massive hotspot. It's a nightmare scenario where one node is literally melting down from the overload, while the other 9 nodes in your cluster are just sitting there totally idle. It completely defeats the whole purpose of having a distributed system.
Which brings us to Section 5, hash partitioning, balancing the load.
So to fix this, instead of sorting by the actual key, we pass the key through a hash function first. Even if 2 input strings are incredibly similar, say 2 timestamps that are only 1 second apart, the hash function scrambles them into completely different, seemingly randomized numbers. We then take those randomized hash values and use them to assign the data to our various partitions.
This makes the hash function the ultimate great equalizer. Because the hashed outputs are uniformly distributed, the incoming data gets scattered evenly across all of the available nodes. Remember that nasty time span hotspot issue we just talked about? Completely resolved. The writes for today's date are now magically spread out across the entire cluster, balancing the system load perfectly.
But as with everything in system design, we have to make a trade-off. Let's contrast these two methods. Key range partitioning is absolutely fantastic for range queries, but it's highly vulnerable to those skewed hotspots. Hash partitioning, on the other hand,
perfectly balances the load, but we completely destroy the natural sort order of our data. If you hash your timestamps, a simple query for all of October's data suddenly requires the database to scatter that request to every single node in the cluster and then try to gather all those results back together. And yeah, that can be terribly inefficient.
Section 6. Matching your workload. Practical synthesis. Let's look at how this actually operates at scale in a massive user account system. When a client requests a profile for a specific user ID, the system takes that ID, applies our hash function to it, determines exactly which partition owns that resulting hash range, and seamlessly routes the request straight to the correct node. It's an incredibly fast, deterministic way to fetch data across millions of users without ever needing to check every single server.
Now here's a totally brilliant workaround used by systems like Cassandra. They use a hybrid approach called a compound key. Check this out. The database hashes just the first part of the key, let's say the user ID. That ensures all the data for that user lands on the exact same node, which balances the overall system load. But the second part of the key, maybe something like an update timestamp, is kept in its natural sorted order locally on that specific node. So you basically get the best of both worlds. Nice, even distribution across your entire cluster, plus the ability to do lightning-fast range scans over an individual user's timeline. Pretty cool, right?
And that brings us to the ultimate takeaway of this explainer. There is no single, perfect, one-size-fits-all architecture. Partitioning is definitely not just about randomly slicing up your data. It's about intimately understanding your query patterns and matching the split to your specific engineering workload.
So, I'll leave you with this final thought. Systems are never static. As your application evolves and scales from thousands to millions of users, what unpredictable future bottlenecks is going to force you to completely rethink the partitioning strategy you rely on today? Keep learning, keep questioning your architecture, and we'll catch you in the next explainer.